Okay, today we're going to be talking about the axioms of functions. So take a mathematical relation like f of x equals x squared. Is this a function? So what we're going to be doing to determine that, or maybe to tell if this function has an inverse function. To determine if a function is a function, we need to determine that it has the property of uniqueness and existence. And then if it does have both of those, we need to determine if a function is bijective or not, usually because if it's bijective, then we know that there's an inverse to the function, which is really useful. So if we have a function, we can determine if that function is bijective and has an inverse if it has the property of being surjective and injective. Okay, so let's go ahead and get into these. So first, we're going to assume that we have a function, and that function is just f of x. All right, so does f of x exist? So existence, it quantifies a statement over the domain. So we say that if a mathematical relation exists, then for every x that exists in the domain x, there exists at least one y in the range, such that f of x is equal to y. Right? So let's take a look at what that looks like. So if we have a domain x and a range y, f of x is a relation that's going to map x to y. So existence is really saying that all of these values have to connect to at least one of these values. So, for instance, something like this is not okay because we have a value here that doesn't get mapped to any value in the range. So that would be a function that exists. And just to be clear, say if f of x was, something like x squared. So say that this is x equals 1, then we would have f of 1 equals 1 squared, which is 1. So that would be this value. So that's what we're talking about here, just in case this is too abstract. So another sort of, I guess, connection that would be allowed in this case is you could also have a value going here. And that's allowed because existence states that every value in the domain has a value in the range. So it doesn't say anything about the range. So this is a function that we could say exists. So let's go ahead and talk about uniqueness. So uniqueness also quantifies over the domain. It says that for every value x that exists in the domain, there exists exactly one value in the range, such that f of x is equal to y. So should probably clarify a little bit with just giving ourselves an example. So given you have a point x and y1 and a point x and y2, what uniqueness is saying is that y1 has to be equal to y2. So what we're looking at, we said that this function is already satisfying the existence property. So for this function to satisfy the uniqueness property, we don't have to change anything here because we can already see that this x value here goes to this value, y value here. That's fine, that's fine, that's fine, that's fine. So where we might run into an issue, let's just create sort of an issue here. Let's see. So let's get rid of this connection up here. And let's say that this value here, can this x value here go to this y value here? So this would be your y1 and this would be your y2. So that's what uniqueness is saying. It's saying that that scenario cannot exist in order for f of x to be unique. So this kind of scenario where you have one x value going to two different y values is not okay if you're wanting the function to be unique. And like we said, this is okay. You can have, for uniqueness, that's fine. You can have two different x values going to the same y value. That's fine. So if we take a look at this function, this is a unique function because it satisfies the requirements that every x value in the domain goes to one unique y value in the range, which is unique to this x value. All right, so now we have shown that this function here it exists and it's unique because it satisfies the existence and uniqueness property of a function. So now we know that f of x is indeed a function. So now that we know it's a function, is it bijective? Does it have an inverse function so that we can go back and forth from the domain to the range and vice versa? So to know that, we know that f of x is a function. Is it surjective? So surjectivity, it quantifies over the range. So it states that for every y that exists in the range, there exists at least one x value in the domain, such that f of x equals y. Okay, so this function that we've drawn here is not surjective because we have some value in the range here which doesn't have at least one x value that it maps to. So we would need to sort of have another point that it could map to that way, and then it would become a surjective function. And I don't see anything else wrong here. Let's see, could it have gone anywhere else? Could it have mapped to a different point? So it couldn't have mapped to this point because then it would no longer be a unique function, because then you would have one x value going to two y values, so that wouldn't be allowed. So yes, we would have to have another point here which connects with this point here. So now we have adjusted this function f of x to be surjective by making sure that there are no points in the range which don't connect to some value in the domain. Okay, now let's move on to the injectivity property, and if we can show that f of x can also have the injective property, then it has an inverse, and it's because then it's bijective. So injectivity property is also quantifying over the range, just like surjectivity. So it says that for every y value that exists in the range, there exists exactly one x value in the domain such that f of x is equal to y. So then, just looking at this function that we have here so far, which is unique, it exists, and it's surjective, what's wrong with it to where it could be injective? Well, the problem is that is just like with the uniqueness property, we'll say that we have 2 points. So they're x1 and y, and x2 and y. Well, injectivity says that in this case, x1 would have to be equal to x2. Otherwise, it's not injective. And so our issue comes with this point right here. So this point right here, we have a y value that goes to two different x values. So it's not injective because of this. So then to fix this, this is the only connection that we have that's a problem. So we can just get rid of that connection. And we'll say there's another point that this connects to. So now this is the only form of a function that satisfies all four properties: injectivity, surjectivity, existence, uniqueness. And this kind of function, it looks very clean. The connections look very clean. They're sort of, for every x you get a y, for every y you get one x. And we call this function bijective. So if f of x is bijective, then what we're saying, let's just clean this up a little bit. If f of x is bijective, then what we're saying is that for a function f which maps x to y, and here we'll say that f is mapping the reals to the reals. So all real values is the domain and all real values is the range. We're saying that there must exist a function f inverse which maps y to x. And the way that we're going to ensure that is we are going to we are going to, well, this is what that would look like given what the symbology that we've used so far for f of x. So if you have f of x, then you have a point in y. So then if you take the inverse of both sides of this function, then you see that the inverse of the function is going to give you x, and that's what it would look like. It would be f inverse of y, because you're taking in inputs of y now, and then that is bringing you to x. And so here we have f of x for our bijective function. Well, your inverse, like your inverse of x, sorry, your inverse of y, is going to take you in the opposite direction. So let's go ahead and take a look at just a function, and we will determine if it is a function, if it's bijective, and if it is, then what is the inverse. So let's do f of x is equal to x squared. So let's go ahead and graph this function. So let's see, is f of x equals x squared, is it unique? So let's start with that. Okay, so if it's unique, then that means that for any one value of x along the x-axis here, let's say this is x, then along this line, you should only be intersecting the relation once, because then that would give you one y value to each x value. So we can see clearly from this graph that that is the case. And one thing I should have done before is just to specify that we're talking about right now a function which maps from the reals to the reals, and from x to y, the domain to the range. Okay, so is it unique? The answer is yes, because for any of these values in the domain, all real values, you're only going to intersect, you're only going to have one value in the range for each x value. So it is unique. The next question is, does it exist? And if it does, then it's a function. So if it exists, then that means that there isn't going to be a value in the domain which doesn't have at least one corresponding value in the range. And we can see that for any real value along the domain, that you are going to have a value. And what we mean by that is it doesn't matter if it's it doesn't matter what value it is. You are going to have at least one value correspond in the range. And I guess if you had a hole here somewhere, then you couldn't say that. Like, say if there was a hole right here in this function, say that, you know, this alternate function is x squared when like for all x except for like when x is, say that there's just a hole here, that there's a hole here where the function doesn't exist, then we would say that this is not a function, because if there's even just one x value where the function doesn't exist, it's not a function. So in this case, for x squared, there's no value where you're not going to get a value in the range. So it exists. So now that we know that it's a function, is it surjective? So if a function is surjective, then we're looking at the range, and we're looking to see, is there any value in the range which does not have a corresponding value in the domain? And looking at this, you might say, no, it looks like, just like with existence, it looks like for every, y value here, I'm going to have an x value that corresponds to it. But actually, that's not true, because the range is also all of these values down here. Because we said that y is, the range is equal to all reals. So here you see that this is the positive reals for the range, and this is the negative reals, and it's all reals for us. So there are some values here for f of x equals x squared in the range that don't correspond to a value in the domain. So we could just write this function off and say, well, it's not surjective, so it can't be bijective. But one thing that you could do is you could alter or redefine the range itself. And you could say, okay, the domain is positive and negative reals, all reals, but the range is just all reals. So then that's just all of these values for the range, like 0 to infinity. So if you alter the range, and you can do that to be all positive reals, then there's no value, there's no y value that doesn't have a corresponding x value. And so this then becomes surjective. And I guess maybe to be more clear with that, that the issue is that, say, if you pick a y value, like y equals -1, right? Like say that this is like -1, y equals -1. Well, what is the corresponding x value? F of what equals -1? And that value just doesn't exist. There is no value for which you're going to get -1 given x squared. So that's what we're saying. And so what we're saying is, if we get rid of the negative values in the range, then it does become surjective. And this is what you see with a lot of inverse functions, like inverse trigonometric functions. You have to sort of get rid of parts of the domain and the range in order to make an inverse function, because then over that range and over that domain that you've altered, it is actually surjective and injective. So to see if this function is injective, we're quantifying over the range, and we are checking to see that there is one value in the range is given one value in the domain. So we are going to take a y value, say right here, and you should see that it intersects with the graph only once. But here we see it intersects with the graph twice. So it does not satisfy, x squared does not satisfy the injective property as is. because x1 is clearly not equal to x2. They're two different values. And injectivity requires that they be the same. So what we could do then is do the same thing we did before, and we call this restricting the domain. So we could restrict the domain to be either positive or negative, and we could make it injective that way. We could make x squared injective if we restrict the domain. So let's restrict the domain just to do something different. It could be positive or negative reals. Either one would work. But let's choose negative reals. So if we choose the negative reals, then that removes all of the positive x values from the domain. And then you can see that now we do have one unique x value for this y value, for every y value, for any y value. There's just one x value corresponding to it. So, started out, x squared defined over all reals is not injective, but x squared defined where the domain is negative reals and the range is positive reals is injective, surjective, it exists, and is unique. So that means it's bijective. And so if it's bijective, then that means that it has an inverse. So first, let's go ahead and draw the inverse. Just kind of clean this up a little bit here. So we know that you can graph the inverse by drawing the x equals y line and just reflecting this f of x function across the x equals y line. So that would look something like that. So this would be f inverse of y. So now x squared is bijective, and this is the function, this is the inverse function. But I've drawn the inverse function, but how would you like solve for the inverse function? So the way that you would do that is we would just go back to what the definition of a bijective function is, which is just that if you take the inverse of the function, then you get back to the domain, and that is your inverse function. So to actually put that into practice, what we're going to do is we're going to take our f of x, which in this case is x squared, and we're going to switch out the variables. And we are going to solve for y, because the idea is that we want to find x so that we can find this f inverse of y. So we want to solve for y, because then we'll switch y back to x. And let's do that. So we're going to solve for y. We're going to have to take the square root of both sides. And then we're going to switch the variables back because I've solved for y. It's still plus or minus y, but I can't make that decision until I take a look at what the domain and the range are. So we're going to switch y back to x and x to y. So we have plus or minus the square root of y is equal to plus or minus f inverse of y. Okay, and to kind of make sure that we need to decide, is it positive or negative on both of these? And so let's just bring down this, because this will kind of guide us and tell us what we need to do. So we have here we're showing that for f, we're going from negative reals to the positive reals. Well, for f inverse, then we want to do the opposites. We want to go from the positive reals to the negative reals. And f inverse is where we're going from y and ending up at x, from the range to the domain. So then just looking at this, we know that this is our x value. So our x value has to be negative, because we're looking at the domain as being the negative reals for this bijective function that we've sort of created. And so by restricting or redefining the domain and the range. So we want the domain to be negative. So that means that we are going to choose the square root of y to be negative, because x is a value located in the domain, and fx is equal to f inverse of y. So we need this to be negative square root of y. Okay, so then we found the inverse. It's f inverse of y is equal to the negative square root of y. And we should be able to verify that this works. And if we look back at our graph, then we can see f inverse of y. It does look like the square root function reflected across the x-axis, because the let's see, the x-axis. So if you have the square root of x, that would be going like this. But instead, you have the square root of y. So that would be reflected kind of like going this direction. But then you have a negative square root of y, which would then, the negative reflects it across the x-axis. So that's how we can sort of verify just by looking at the graph. But we can also just take a look at what we've got and just plug in some value. So if I have like, let's see, if I have f of x, say this is x equals -2, then for x squared, f of 2 is, or sorry, f of -2 is equal to -2 squared, which is equal to 4. So then I have here my value in the range would be y equals 4. And from this function, I want to get back to -2. So then f inverse of -2, or sorry, f inverse of 4 is equal to negative. square root of 4, which is -2. So we know that this works. Um, and yeah, I hope this was helpful. If you like this kind of content, let me know, and I can go more into functions because it's actually it can actually get pretty complicated, and I think it's a lot of fun. So thank you so much.